Hello, this is Megan Adekary from Lab Section M01, and I will be discussing Lab 7 Black Hole Mass. The objective of this lab was to calculate the mass of a black hole around which a star orbits. The position of the star was tracked over a set period of time and then inputted into VPython to model its motion. The data was also used to calculate the net force on the star, and this net force, which was the gravitational force of the black hole on the star, was then used to solve for the mass of the black hole. And after all this was done, the program was able to calculate the mass of the black hole. As any other object, before we could model its motion, we had to set some initial conditions, such as the mass of the star, which was 1.989 times 10 to the 30th kilograms. We also had to input the position of the black hole, which was given. Also, because we are tracking a star, delta t is the number of seconds in a day, which seems big but is actually small in comparison to the time of the star's orbit. Then, in order to model the star's motion, as well as calculate the black hole's mass, we had to calculate the star's velocity, which was calculated from the position data. The calculated velocities were then used to calculate the star's momentum. Now, because the star is orbiting a black hole, its motion is circular, or rather elliptical. So the net gravitational force acting on the star is made up of forces that are either perpendicular or parallel to the star's motion. These are F net perp and F net par respectively. Although the decomposition of the net force is not needed in the calculation, it helps show that the net force is the gravitational force exerted on the star by the black hole. Once the net force was calculated, it was then inputted into the gravitational force equation, and then we solved for m2, n sub 2, which was the mass of the black hole in this case, where capital G is the gravitational constant and r is the distance between the star and the black hole, the radius of the star's elliptical orbit. And so this is the model. And as you can see, there are three arrows. The red arrow represents the net force in the perpendicular direction, which is perpendicular to the star's motion, which is in this case towards the center of the circle. The green arrow is the net force in the parallel direction, which is parallel to the object's motion, and the blue arrow is the net force acting on the star. And as you can see, it points toward the black hole. The program then outputs the star's mass, the total time of the orbit, and finally the black hole's mass, which was 3.184 times 10 to the 31st kilograms, which is correct as compared to a known value and that was checked through WebAssign. But now to the main reason behind the objective of this lab. We'll look at the method used to model the object's motion. We used the position data to calculate the velocity, which was used to calculate the star's momentum. The momentum principle relates the change in momentum over time to the net force, as dp dt equals F net. However, just like real objects, the net force on the star is not constant. It changes as the distance between the black hole and the star changes, shown by the equation for gravitational force. F net equals capital G times m1 m2 over the magnitude of r times r hat. That is why we had to decompose the net force into the sum of the forces acting on the star, both perpendicular and parallel to the star's motion. And since we used the momentum principle initially, both F net parallel and F net perpendicular are numerically equal to dp dt parallel and dp dt perpendicular respectively. However, although they are numerically equal according to momentum principle, F net, dp dt, and their components are not the same. They are related as a change in momentum implies a force was acting on an object, and a net force implies that there was a change in momentum of the object. But they are just different perspectives to understand why an object moves the way it does. So finally, to the what if question. If a different black hole replaced the original black hole, keeping the same initial conditions, would we calculate a different mass for the replacement black hole? Well, if the position data differed in that the numbers were different, but the motion was elliptical, then yes, as different numbers would change the resulting velocity, momentum, net force, and the distance between the star and the black hole, which would result in a different mass. But if the position data was the same, then the mass would have to be the same, as the resulting numbers would be the same as the initial condition that we had here, So if the position data was the same, then the mass would not be different. Thank you.